than this parameter, we will compute the updated area of the plant by using this equation. The area of plant required is previously determined, that we have determined by this equation. So once we have determined the area of the plant, so we are equating the lambda f value, which is equal to bf over 2tf value, with lambda p to compute the width of the plant. So lambda f value is equal to bf over 2tf value. So we are multiplying and divided this factor by bf, and we are equating that our plant should be compact. Anyhow, they may be non-compact, but we are determining the bf value by assuming that plant would be the compact. So bf is multiplied with the bf, that is equal to bf square, and bf into tf will be multiplied, so that is equal to area of plant. So if we are bringing the 2 times of lambda to the other side and taking the under root, so we can determine the width of the plant by this expression, by equating the slenderness ratio or B over T ratio of the plant with lambda p. So lambda p value is equal to 10.8 for the compact plant, and lambda r value is computed by this parameter, which is 19 for 8 30 60. So I have already explained. So after determining the bf value, the width of the plant should be between h by 3 to h by 6. So width of the plant should always be more than h by 6. So why? If the width of the plant will be lesser, so it will have lesser moment of inertia about y-axis. So bf value should be rounded to the nearest multiple of 50 mm. So whatever is the bf value, we will round it to the multiple of 50 millimeter to the nearest side. So once we have determined the bf value, so area of the plant will be divided with the bf value, and we can determine the thickness of the plant. And after determining the thickness of the plant, if the thickness of the plant is less than 10 millimeter, so it should be the multiple of 2 mm. For example, if the thickness is coming out to be 7.3, so we will round to the multiple of 2 millimeter on upper side, so we shall use 8 millimeter. So if the thickness is 8.4, so we will use the thickness of the web as a 10 millimeter, multiple of 2 millimeter on upper side. But if the thickness of the plant that we have computed from this expression is between 10 mm and 40 millimeter, then it is selected in following order to the upper available size. For example, this equation is giving the answer 12.7. So the available size on upper size is 15. If thickness of the plant is coming out to be 16, so we shall use the thickness as a 18. So if the thickness is coming out as a 15.3, we shall not use 15, because we will select to the upper available size as a 18. And if this formula is giving the answer more than 40, then we need to select the thickness of the plant in a multiple of 5 millimeter on upper side. For example, if answer is 41, so we shall select the thickness as a 45. Or if the answer is 54, we shall select the thickness of the plant as a 55. So after computing the thickness of the plant and the width of the plant, we shall check the lambda f value by bf over 2tf, and this value should be less than lambda r. So plant cannot be non-compact. Okay, further I will explain here. The moment carrying capacity is determined by either this formula or this formula. Once we have decided the web and the flange size, next check is we need to validate the capacity, or we need to verify the movement carrying capacity, whether the movement carrying capacity is more than applied load or not. So movement carrying capacity will be depending upon tension flange. So movement carrying capacity formula is this one. Mu is equal to 5Bmn. So we can say that this bending stress is My. So sigma y, we are representing as Fi is equal to My over I. Or I over y is equal to section modulus. So Mu will be equal to 5Bmn will be equal to 5B into Fy into Sx. So nominal movement carrying capacity is equal to Fy into elastic section modulus about the x-axis multiplied by its 5B value. So we are exactly having this formula. So for doubly symmetric I section, the tension flange, because the flange which is in tension, it will always be stable. So it will never undergo buckling. So nominal moment carrying capacity will be this one. But when a beam is subjected to applied bending moment, so one side is in compression, so the flange which is in compression, it may undergo buckling, because whenever any structural component is subjected to compressive force, so it is undergo buckling. So we can determine the capacity with reference to compression flange by multiplying the section modulus with reference to the compression flange and FCR. So FCR value is the critical stress at which the buckling in compression flange will occur. So FCR value is the function of two parameters. One, with reference to lateral torsion buckling. Lateral torsion buckling means that this is the stress value at which the member will start twisting in the lateral direction. So which is the function of the unbraced length, which is we are determining in beam. So other thing is that I told you in the start, our flanges, they may be compact or non-compact. So if flanges, they are non-compact, it means that the flange, they can also buckle at a stress value less than FCR. And RPG value is the moment carrying capacity reduction factor, which is depending upon thin web. So section modulus, first of all, how we can determine? I will explain. Section modulus we can determine by, if we know the moment of inertia and divide by the y value. And RPG value we will determine by this parameter, this equation. You don't need to memorize because all these equations, they are given in LRFD design aid, page number 320. Yes, here. And RPG value, yes. Page number 322, and the formula is given. So in this formula, we require AW value, HC value, clear depth of the girdle, thickness of the web, 2.7 time into E over Fy, and AW can be computed by this parameter, which is the ratio between the area of the flange to the area of the web to the area of the flange. And FCR value, yes, how we will determine? So FCR value that I have just explained over here. Actually, we always determine the moment carrying capacity by this formula, because this formula will always give the lesser capacity, because compression flange will always buckle before yielding will occur in tension flange. So we need FCR value. So FCR value, one FCR value will be based upon lateral torsion buckling, and one FCR value will be based upon flange local buckling. So we shall determine one value from here and one value from here. Whichever will be lesser, that will be used in the formula. So FCR value based upon later torsion buckling is will be determined by by using the factor LP and LR. So we will compare the unbraced length against LP and LR to check the class of the beam section depending upon later torsion buckling. If unbraced length is less than LP, so our beam will be compact with reference to later torsion buckling. So FCR value will be equal to F1. So if unbraced length is more than LP but less than LR, so we shall use this formula. So this formula is same that you have been using in beam design. But if unbraced length is more than LR, so our beam will be cylinder with reference to later torsion buckling. So we shall use this formula. So depending upon the class of the beam section based upon later torsion buckling, we need to use any one of the formula to determine FCR. Similarly, out of these three formulas, this formula will not be applicable because our flange will always be compact or either non-compact. So we will check the lambda f value with lambda p. If lambda f pf over 2 tf value is less than lambda p, which is 10.8, then our flange will be compact. So flange will always fade due to yielding. But if lambda f value is more than lambda p, but less than lambda r, so we shall determine the FCR value based upon this parameter. So this equation and this equation is almost same. What is the difference? Wherever we are having the unbraced length, we are having the lambda f value. Where we are having the LP value, we are having the lambda PF value. And where we are having the LR value, we are having the lambda RF value. So only the unbraced length is changed with the lambda value. So after determining the FCR value, we can compute the moment carrying capacity. Okay, next question is that actually we are provided with the LV value only. In beam design chapter, we actually consulted the LP and LR value from beam selection table for any standard steel section. LP and LR value they are given, but plate girder is not the standard section. So it means that for plate girder we need to determine the LP and LR value by ourselves. So we are having the expression for LP and LR value. LP value is 1.1 times of RT under root E over Fy, and LR is pi RT under root E over 0.7 Fy. And for a 3060, E value 200 gigapascal or 200,000 megapascal divided by 250. For a 3060, LP value is equal to 31.1 into RT. So this will be in millimeter. So by dividing 1000, we can convert into meter. So similarly, LR value for a 3060 is 106.2. It means that if we want to compute LP and LR value, we must know RT value. And what is the RT value? That is the radius of gyration of compression flange plus 1 by third of compression web, which is taken about the y-axis. So last time I have explained, so we are having two formula, either using this formula or this, because this formula is simplified from here. So we need to compute RT value by using either formula. So we know the width of the compression flange. AW value is the ratio between the web area to the flange area. So this value is already also given in LRFD design aid. So lambda p value is 10.8 for 836 days and 19 for 836. Otherwise, we have to compute. So RT value formula is also given. By using any one formula, we can determine RT value. And if we know the RT value, we can determine the LP and LR value accordingly. Similarly, based on later torsion buckling, formulas are also given. And based on plain local buckling, formula for FCR value, they are also given. So if the moment carrying capacity is more than applied load, then that is okay. Then I further explained that we always determine this section or flange dimension and the web dimension based upon maximum bending moment, which is just produced on the central portion. So we can economize our beam section along the length for different bending moments. For example, we can reduce the flange area or the depth at a section where the moment is lesser or M1. So by using the M1, we can resize the flange dimension or the web dimension. So that I have already explained. And maybe at section 2, we are having lesser bending moment. So maybe we require only one plate. Or maybe in this portion, moment is larger, so we require two flange plates. And in the center portion, we require a thicker flange because moment is larger if we are keeping the depth as a constant. So we can reduce the flange area either reducing the thickness of the flange, width of the flange, or depth of the web that I have already explained. So we can further customize our plate girder depending upon the applied bending moment. Okay, next we shall start the problem and we will cover just overview, and next time we will study this problem again, but let me explain the some data. So statement is that proportion of plate girder with a span of 20 meter to support a factored UDL load of 70 kilonewton per meter. In addition to self weight. So self weight is not included. We need to assume the self weight. So factor load is 70 kilonewton. And two factored concentrated loads of PU magnitude is 750 kilonewton, and each load is located at a distance of 7 meters from the roller and hit support from either end. The compression flange is laterally supported at ends. So bracing is provided in the lateral direction at ends and at the point of concentrated load, maybe with the help of secondary beam or by any way. And girder is unsheltered. So why this information is given? Because this information will be used to decide the thickness of the web based upon Killian phenomenon. So first of all, let me explain the problem from the figure. We are given this plate girder. Total length is 20 meters, 7 plus 6 plus 7. So it is subjected to a UDL load of 70, not 76.9. Why this is 76? Because it including the self weight. So total load of 70 kilonewton, a UDL load is acting. And 2-point load each of 750 kilonewton, they are applied at a distance of 7 meters from either end. Maybe one from the end A and other from end D. Magnitude of the both load is 750. And we are also given that beam is braced at point A, D, which are the supports, and at concentrated load points. So I have shown these 4 points, 1, 2, 3, 4, which are laterally braced points. So based upon lateral bracing, we are having three segments, AB, BC, and CD. So we need to design the beam for the critical segment. So that we will decide. So first of all, we need to assume the self weight. So self weight can be assumed or determined by using this formula, 0.013 into mu power 2 by 3 or 0.67. Again, I guess this formula is provided in LRF. We design it. Let me check. Yes, self weight formula is given. So here, this mu, this is the moment, maximum moment without self weight. So this you can determine maximum bending moment by determining the maximum bending moment over here. So you can determine by any method. So this load you will assume as a 70.6. So you can split up this beam into two parts for simplification by using principle of superposition. One beam is only subjected to load 70 and one beam is subjected to only two concentrated loads. You can determine the maximum bending moment in the center and then you can add both bending moment to compute the maximum bending moment due to combined loading. But anyhow, reaction maximum bending moment due to UDL load will be omega L square by 8. That I have determined, omega L square by 8. And due to the concentrated load, it's assumed that this beam is subjected to only load 750 and 750 K. The loading is symmetrical, so each reaction at point A and D will also be equal to 750. Because loading is symmetrical, so each reaction will be equal to half of total loading or equal to the single point load. If this load reaction is 750 on the upper side, so you can determine the moment of this load 750 multiplied by this distance 7. So you shall have the maximum bending moment at point B. And moment will be remain constant from B to C due to concentrated force. Or what you can do, you can determine the maximum bending moment in the center by plotting the shear force and bending moment diagram. So if your concepts are strong, then you can also determine by simple method. So this is the maximum bending moment, which is 8750 without self weight. So we shall use this value in this equation in kilonewton and meter. And when we determine the answer will be 5.7 kilonewton per meter. So assumed self weight will be equal to 5.7 kilonewton per meter. So this load is unfactored. So this is a dead load. We will convert this load into the factored load by multiplying with the overloading factor 1.2. So 1.2 is the overloading factor we are using. So we are converting the dead load into factored load, which is 6.9. Okay, now we need to add this 6.9 load into the total applied load because self weight is the distributed load. So we will add this 6.9 into 70. So total applied factored UDL or uniformly distributed load will be 76.9. So now we have updated the loading, including the self weight, and point load will be remain as it. So after considering the updated loading, we need to determine this force reaction. Force reaction will be equal to omega L by 2 plus this P load, which is 1519. So you can plot the, because if you can determine the shear force and bending moment diagram by principle of superposition, that is well and good. But if your concepts are not so strong, so you can plot the shear force diagram and bending moment diagram by using the knowledge of your mechanics of material and structural analysis. So maximum shear force in this plate girder is 1590. Bending moment is not, although the bending moment is 8749 at B, but the bending moment diagram is not uniform. So moment is changing from 0 to maximum value. But this center span, it is subjected to minimum moment of 8749 and maximum 9095. So I'm assuming that segment B and C, whose unbraced length is 6 meter in lateral direction, is the critical. So we shall determine the height of the web by using this formula, which is also given in LRFD design 8, 1.1 time of mu power 1 by 3. So in this formula, movement must be in Newton and millimeter. Then we will have the height in millimeter. So we are multiplying it with the exponent 6 to convert the movement from kilonewton into meter to Newton and millimeter. When we got the answer is 2296. So we will round this value in a multiple of 25 mm to the nearest side. So the answer will be 2300. So we have fixed the height of the web as a 2300. After that, we shall determine the thickness of the web. So thickness of the web will be provided corresponding to minimum thickness. So minimum thickness of the web is determined by three equations, so three formula, or by three criterion we have already studied. So TW1 is based upon corrosion resistance. We are given unsheltered condition, so this value will be 10 mm. Second, depending upon the web buckling, assuming that A over H ratio is more than 1.5, or we are providing the stiffener at a spacing more than 1.5 time of the H. So second is H by 320. Height of the web we have already computed. So divided by 320 is 7.9. So maximum shear force, third thickness is based on maximum applied shear. So you can either use this formula or simplify this formula for a 3060 we have discussed. So VU value is in kilonewton, 1519 we have just determined, divided by height of the web. So thickness is coming out to be 8.2. So out of these three values, larger value is 10 mm. So we are going to use the thickness of the web as 10 mm. So this provided thickness we need to compare against the TW maximum. This thickness should be less than maximum thickness of the web that we may provide. So TW maximum is equal to height of the web divided by lambda R value, or lambda 161.2 for a 3060, to make sure that web is cylinder, so which is 14.27. So the thickness of the web that we are going to provide is less than TW maximum, so that is okay. Okay, in case if this value is coming out to be 15, which is more than 14.27, so we cannot provide the thickness of the web more than this value. So what we can do, we can select the TW maximum as our provided thickness, or we can increase the height of the web. from 2300 to maybe 2350, maybe 2400. Because if we are increasing the height of the web, then we will have the lesser thickness. Because if we are dividing, then we can reduce the thickness. We shall see in some of the examples. So web size is coming as 2300 into 10 mm. So next is we will decide the flange dimension. So for the flange dimension also we are given the formula. Let's see where the formula is given. Yes, this one. So we are using this formula. So in this formula, mu is in Newton and millimeter. We are substituting the value 90, 195 divided by 2300 is the height of the web minus area of the web that we have just computed, height of the web into thickness of the web divided by 6. So area of the flange is coming 1543. So we need to check the condition. So we will compare this parameter with LB. So LB is 6 millimeter for our center span, which is critical. So 6 meter means 6000 millimeter. And at the start, we may assume CV value equal to 1. So this is the area of the flange that we have just computed over here. So we are going to compare this right hand side with left hand side. So this answer is coming 5236, which is less than 6. So it means that this condition is not satisfied. So we need to revise the area of the flange by using this equation. So this equation is also given in LRFD design. So we shall revise the area of the flange. So area of the flange required is previously determined by this equation. CV value assuming 1, LB of the given segment 6000, 1543. So actually you can also substitute the actual CV value. I will explain when we are going to check the capacity. So BF value will be computed. So updated area of the flange is coming out to be 15,943. So BF value is determined by using this equation that we have already derived. So lambda P value actually here is 10.8. Better to use 10.8 for the flange. And the answer is coming out to be 586. So BF value should be the multiple of 50 mm to the upper side. So when we round this value to the multiple of 50 millimeters, the value is 600. We need to make sure that the width of the flange is more than height of the web divided by 6, which is also satisfied. And next is we will compare the thickness of the flange, which is equal to area of the flange divided by BF value that we have just divided. So area of the flange divided by BF value, answer is 26.57. So available size on the upper side is 28 millimeter. So after using 28, we need to determine the lambda value, which is BF over 2TF. BF is 600, 2 times of thickness of the flange, answer is 10.7, which is less than lambda. It means that our flange is not cylinder. So because flange may be compact or non-compact. So lambda R value, how we are got this 90? Because lambda P is 10.8 for a 3016 and lambda R 19 for a 36. So lambda P, lambda F is less than lambda R, so flange can be used. So I will stop here. So next time I will explain how we can determine the capacity after deciding the flange and the web size. So at the moment, if someone is having any question, he can ask me. So CR, there will be no design class today because I have a meeting, so I will be busy. So inshallah next time we will have our lab design class where I will explain
Okay,
how
sir.
to sketch the steel design sheet. Okay. So
Okay, sir.
please raise the hand, all the students who are present. So engineer Ehtasham, Ehtasham, अब समरवान, इसको किसने मैसेज कर दिया भाई आ जाओ जल्दी से ऑनलाइन। ये दो हैं, ठीक है। ये कौन है? एफ के,
सर फैसल है इसका नाम।
ठीक है। इसका और ये नोट करो, ठीक है। एंड दे विल बी
ओके
मार्क्ड
सर।
एब्सेंट। मैं आपको कैंडिडेट सारे भेजूंगा इंशाल्लाह आज, ठीक है। ओके,
ओके सर।
सी यू द नेक्स्ट टाइम। अल्लाह हाफिज़।